Hello again. This is Math 2233 coming to you from the College of DuPage, and the title of this is Double Integral Applications, Moments, and Center of Mass. And as always, please be an active learner as you watch this video. We've seen a couple of applications of double integrals already, computing volumes and finding surface areas. And in this section, we'll talk about some physical applications, computing mass, electrical charges, centers of mass, and moments of inertia. And we'll have one other application that I think we'll talk about in the future, and that's going to be probability density functions of two random variables. Lots of applications of double integrals. Let's continue with density and mass then. So earlier we were able to use single integrals, depending on who taught your Calc 2 class, to compute moments in centers of mass of a thin plate or lamina that had constant density. But now, since we have double integrals, we can talk about actually having a variable density. And the variable density in this case is going to be called rho. So rho at xy is going to be the limit as delta A goes to 0 of the mass over the unit area. And that's going to be the density function. It's a variable over this region D. So to find the total mass of the lamina, we're going to divide the rectangle containing D into subrectangles Rij of the same size, and we're going to consider rho to be 0 outside of D, and we choose a point in each one of those little sub rectangles, and the mass is going to be, you add all those up, the density times the area, and that's going to give you mass, the change in mass of that because of this equation up here. So if we add up all these masses, we get an approximation of the area, and in the limit, it's going to be the total mass. So here we've divided into rectangles, and here's the resultant integral. So what we find is that the mass is the double integral over the region D of the density rho of xy dA. Now physicists also consider other types of density that can be treated in the same manner. And so, for example, if an electrical charge is distributed over a region D and the charge density in units of charge per unit area is given by, this is a different Greek letter, this is sigma. So this is sigma of xy at a point xy, then a total charge in the same way that the total mass is. The total charge would be the double integral over D of sigma of xy dA. So here's a problem for you to do. Charge is distributed over the triangular region D. This is the triangular region D. This point, of course, would have to be 1, 0. So that the charge density at xy is sigma of xy. And now we have an explicit expression for this. This is xy, and this is measured in coulombs, the unit of charge, per square meter. So you find the total charge on this triangular region. You know what to do. So let's see how you did. All right, so we have that the total charge is the double integral over D, sigma xy dA, and this is the triangular region, and I'm going to fix it this way so that x is fixed. That means I integrate with respect to x second, so I'm integrating with respect to y first, and I can see that for this fixed value you go from 1 minus x to 1, and those are your limits of integration, and then you go from 0 to 1. So first we integrate with respect to y, keeping x constant, we get this, and then this. And then we expand this and simplify it. We can pull out the factor of 1/2. And we end up with this. Once we do the simplification, you should really check all of these calculations yourself. I will expect you to do these calculations. Then we integrate this expression in x from 0 to 1, and we get 5 over 24. So that means that is the total charge over this area is 5 over 24 coulombs. Let's turn our attention now to moments and center of mass. Now previously we found the center of mass with constant density, but here we're talking about the variable density. So we have a function that is rho of xy where the density varies. So what we're going to do is we're going to be looking at the mass, which is approximated by this, which is rho x star y star delta A, and we approximate the moment about the x-axis by the distance from the x-axis, which really is going to be the measure of y at that point. So this is the moment in that small little rectangle, but if I add up all those little rectangles, I get this. So the moment about the x-axis for the entire lamina is given by the double integral over dy rho xy dA. Similarly, the moment about the y-axis is given by, and again, this is going to be the double integral over the region D, and this is going to be x times rho xy dA. And as before, the importance of the center of mass, which often is called x bar, y bar, is that that will give you the point over which, if you put it on a very sharp pencil, you could balance it, because the moments in the x and y directions are equal to each other, and so that means it can balance there exactly. Now, from the theory that we've talked about then, x bar is going to be found by the moment about the y-axis divided by m. So it's 1 over m times this integral. And y bar is the moment about the x-axis divided by m. So it's going to be 1 over m times this integral. And to find the mass is this integral. Now this is a very common assessment problem that gets asked, so make sure that you know how to do this, and there are 3 integrals that you ended up computing. One for the mass, one for this moment, and one for this moment. So here's the problem. Find the center of mass of the triangular lamina with vertices this in the xy plane if the density function rho of xy is 1 plus 3x plus y. You know what to do. Let's see how you did. First we compute the mass. That's the double integral over d of rho of xy dA. Now here is the region D that we saw before, and so this region D then, and here we're integrating with respect to y first. That means we fix x. So we go from 0 up to this, and this is 2 minus 2x. So that's the first integral, and then we integrate from 0 to 1. And so we perform the integration, and we get 8 over 3. So the mass is 8 over 3. Now when you look at 1 over 8 over 3, it becomes 3 over 8, and then this is the moment about the other, this is the moment about the y-axis, and so we multiply all the way through using our formula, and we compute this double integral. And at the end of this we get 3 over 8. Now that means this is x bar. Now y bar can be found in a similar fashion. We do the calculation down here for y bar, and we will get y bar, and we do the same thing with the 3 over 8, and we get 11 over 16. So the answer to this problem is the center of mass is 3 over 8, comma 11 over 16. Make sure you can follow these calculations. And let's try one more problem. The density at any point on a semicircular lamina is proportional to the distance from the center of the circle. Find the center of mass for this lamina. You know what to do. Let's see how you did. Okay, we are free to choose where we put the semicircle, so we put a general semicircle this way. We go from minus A to A, and that's what we have for that. When the density is proportional to the distance from the center. The center is 0, 0, so that distance is the square root of x squared plus y squared. So this row is proportional to the center. I put that in, and then this is best done in polar coordinates. So dA becomes r dr d theta, and square root of x squared plus y squared becomes r. I calculate it, and this is my mass. I compute y bar and x bar. And we can note that the x bar, because of the symmetry of both the density function and this, the center is going to be the geometric center. So at the end we get the answer is 0, 3a over 2 pi. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. May God bless you all.